Good morning, everybody. Today, I will be presenting a recent paper from IJCAI, which is titled Against Membership Inference Attack, Pruning is All You Need. This paper was mainly written by folks from UConn and Duke University. Here's a brief agenda of today's talk. First, I'll speak about some motivation and introduction. Then I'll speak a little bit about the membership inference attack. Then I'll explain the core of this paper, which is the pruning is all you need concept. Then I'll speak of some theoretical analysis, followed by some experiments, and I'll finally conclude the paper. Starting off, we know that the success of modern deep neural networks is mainly dependent on the vast available data and the advanced computing power that is available these days, so which makes it possible to apply in several different applications like facial recognition, smart healthcare, etc. However, due to its very large model size and very high computational operations, the deep neural network's popularity has been impeded a bit, especially when it comes to applying it on smaller resource-constrained devices such as mobile devices. One small option that was introduced to overcome certain challenges of implementing the machine learning models and training bigger models was the machine learning as a service platform. This is a viable solution which basically reduces the overall cost, and it is a scalable and a flexible paradigm. I'll speak a little bit more about the MLAAS platform. So the Google Cloud or Microsoft Azure or the Amazon Web Services or many such service providers have come up with the MLAAS platform where they provide black box interfaces. So using those interfaces, either companies or groups of individuals or just any individual could use some analytical services as a pay-as-you-go or a subscription kind of a service using mobile devices or personal computers, where you can you can use your own data set and use their cloud service to train very powerful large-scale DNNs. So that way you do not have to worry about training parameters, the hyperparameters, or how you would be hosting such big models, but you can still be able to achieve what you want of giving the data and receiving the prediction tasks or classification or any such outputs that you need. So MLAAS has been really popular because of its very easy to go approach. However, there are certain challenges when it comes to using the MLAAS as a service or just using the large neural networks on smaller devices. First is the privacy concerns. When you have sensitive data such as the medical records, like the patient treatment records, it becomes really risky to be using such open source cloud services because the MLAAS especially can leak certain sensitive information about the training data because those are used to build the backend models which are required for training. Also, as we know that for usage in wider applications and faster applications, the DNN models are really evolving fast because they want to involve some diverse characteristics because they want to cover so many applications. So because of that, the size of the deep neural networks these days are becoming very large because the number of layers are getting very deeper, and hence the overall size is becoming very large. So because of this, there are large computational operations that are involved in it. And this model, the huge model size also introduced some substantial data moments. This limit their ability to provide a very user-friendly experience on smaller devices such as the mobile devices. So to overcome these challenges, this paper tries to introduce a concept. But before I jump into it, I'll speak a little bit about the membership inference attack. So in the membership inference attack, as we can know from the name, it is an attack. So it is performed by a malicious client, and the attack time will be, as the name indicates, it is during the inferences when this attack happens. And the main goal is to compromise the training data privacy. So any adversary wants to know if this specific data record or if a particular data record, let's say X, was part of this model's training data or not. So it wants to know whether there was a membership of this particular member or not in the data set. So let's say that we have the training data here, and which is used to train a model, and the predictions are performed. And the adversary tries to use this model in the inference stage, and he tries to put some input, give some input data, and wants to see what's the classification like, through which he'll be able to determine whether the target that he's specifying, let's say, for example, the automobile with this particular car is in this training data or not. So what kind of capabilities does our adversary have to perform this sort of an attack? One is we assume or we see that he has a labeled data record access like XY, a small one, one or more samples of it, he might have some access of it. And then the adversary also has the capability to perform a query, model query across the machine learning as a service platform. So using which he can be able to obtain the prediction vector y for a given x. And we also see that, assume that he would, for this paper, we assume that the adversary has a black box access to this machine learning as a service kind of a platform that was used to train the model. While it does not necessarily have to be just a black box, there are certain cases where even the white box access can be available and the adversary can successfully still be able to launch the attack. But the black box, while white box, the adversary would know what kind of model is being trained. He would also have some access to some kind of parameters. So that is a more open setup. So a little more harder to attack would be the black box setting, where all the internal working of the model or what kind of model was used. So anything inside the machine learning training the deep neural networks would be totally unaware. So that is something that the adversary wouldn't know. So that's why we categorize this kind of attack as black box attack. So let me speak a little further about how this kind of attack works. The intuition is that machine learning models usually behave differently on data where they were trained versus any unseen data. So let it be a test data or some portion of the training data set which was not used for training, but it was produced to the machine learning models later. So the intuition is that for unseen data, the performance would not be that great. The behavior will be a little different. So, and overfitting is one of the main reasons why we see such thing happening, where the training performance, the training accuracy may be very high, but when the model when the model tries to do the predictions over unseen data, the performance may be very, very bad. So overfitting is one of the basic reasons. So this is one main factor that any attacker can leverage to learn the difference between how a machine learning model behaves when it is trying to do inference over seen data versus unseen data. So for an end-to-end attack process, let's say the adversary uses a labeled record XY, and they use a target model F, like for example, this model, let's say this is called F here, just the machine learning model which was trained. So with this labeled record and using such a model, the adversary will be able to compute the prediction Y, which is nothing but f of x. So so the adversary will use his own model, an attack model FA. If you look at the main membership inference attack papers by Shokri, the first paper, they use a shadow model, which is kind of trained simultaneously during the actual training. So the adversary will maintain his own small copy, some shadow model that he'll keep training. And at the inference, he'll use that to perform the attack and to get the membership details. So such kind of a model is the attack model FA that the adversary will use. So in the process, he will be receiving both the true class label Y and the prediction vector Y. This is because he is using the MLAS as a service. Because he would have subscribed, he can behave that he is the main user, and that's why he can get the predictions and the true class labels as well. So then FA computes the membership probability to see whether the label record that he's targeting is present in the data set or not. And so this is kind of how the membership inference attack works, basically. So to avoid such security vulnerabilities, many popular defense mechanisms that we've seen in the literature are differential privacy, game theory, or the pruning. So in the DPA, the differential privacy, we know that it's a really popular major privacy preserving mechanism. And generally against the general inference attack, this can be used. However, the disadvantage of that is that the utility cost is hard to be limited. Plus, it also imposes a significant accuracy loss if you have to protect some really big and complicated models, because the privacy budget is going to be a lot more, so the accuracy loss. So there's a trade-off between the performance accuracy and the privacy protection that it provides. So the other popular method was the game theories. For example, let's say the min-max, where it is where we try to minimize the worst possible maximum gain of a model, or the maximum models where you try to maximize the minimum possible loss. So in this paper, they considered the example of min-max. So in that, we know that it tries to guarantee some information privacy by using the fact that it can try to use the worst case scenario of the maximum gain of inference of the model can be minimized with the training model loss. But the disadvantage of using game theory methods here would be that it introduces some extra computational operations other than just the classifier training. So this is a small caveat that this process has. So the other method that this paper thinks that can help us to provide some defense is the weight pruning. So weight pruning is a method where a significant amount of your network is removed by removing the weights with certain specific dimensions, or you can provide, say, any desired weight matrix shape. Based on that, the remaining weights will be pruned. Or you can also say the desired number of non-zero weights that you need in each layer. So the remaining weights will all be removed, or they'll be basically set to zero. So this is how weight pruning works. So using this concept, let's see how this paper tries to defend the model inversion attack. So the basic idea is that they simultaneously try to address both the large model size that do not fit over mobile edge devices concept, plus the high computational cost it incurs. Along with that, the vulnerability against the model inversion attack, which I've abbreviated as MIA here on the deep neural networks. So the whole idea is to find a subnetwork that can prevent any privacy leakage from the model inversion attack and also achieves some competitive accuracy. So if you have a training data over here, you have a classifier, the main classifier, and we perform the weight pruning where certain weights or connections that are not important to us are removed. So you have a smaller version of the model, and f of x will be your prediction that is received. So let's say that you have an adversarial access who is using the MLAES service, and he gets access to this, and he tries to look at the predictions and to get the prediction as well as the ground truth value here to be able to use a probabilistic prediction to see whether the one of his interest is in the data set or not. So for that, they also use a non-training data, the one that is unseen, to see how the model behaves when it is working with a unseen data and tries to get those predictions. And using that, it tries to see whether the person of interest is present in the data set or not. So I'll explain how the problem is formulated using the pruning. If you see the main membership inference attack papers, they claim that one sort of defense mechanism to avoid this attack is the dropout. So if you can drop out certain neurons, then you may be able to avoid the overfitting issue. So because you avoid overfitting, the predictions that come out of the training data and the non-training data, so the difference between them will not be a lot. So that will avert the model inversion attack. So using the same concept, this paper tries to extend it to pruning, and they also give us the theoretical explanation for that. So the problem is formulated in this way. First, they try to describe the gain function of the
Pavana, can you just go back to this slide? So
yeah.
So FA. So FA is the attack. This is the attack model they are trying to learn, or they want to train an adversary attack. So
Okay.
what's this one?
Okay.
I assume you mean they are trying to defend, or they are trying to find the best weight pruning method, right?
Yes. So what's the role of this FA over here is to they find it's like to find the worst possible attack possible, the FA. They first find FA in such a way that that will be the best kind of attack, and then they try to find a weight pruning model in such a way that that will defend the FA from happening.
Oh, okay.
That's how they
So
strengthen the F.
Oh, so this is more like they want to find the best with pruning method. However, in order to find this best one, they want to come up with most powerful adversary. So
Yes.
that's why so this is more like a game.
Yes, they kind of, yeah, they have like two methods in it. One is without using the game part, and one is with using the game theory kind of way.
Oh, okay.
Yeah.
Okay, I see. Thanks.
Yeah. So let's look at the problem formulation. So G is the gain function. FA is the adversarial model, which they will use at the inference, but we also would try to train this to find the best possible FA in the process. And using the classification model FX, the target model, we try to define the gain function as the expectation of the logarithmic of this plus the expectation of log of 1 minus FA. The first term here is nothing but it implies that the inference model's accuracy in predicting the training data would be this. And the second part of the expectation function is nothing but accuracy of the inference model on predicting the non-training data. So this is versus the training plus the non-training data, the unseen data. So we basically want to find the difference between this. So as I progress, maybe I can explain it even in better detail. Here, D is nothing but the training data set, and the D prime is the non-training data set or the unseen data or the test data, or you can think of it of anything like that. And PD and PD prime are nothing but the probability distributions of the samples corresponding to these training data sets. So the first method that they propose is called the MIA pruning, which is the model inference attack pruning against the model inference attacks. So the objective is that they want to have the model predictions for the training data set and the non-training data set. They should not be distinguishable, because if there's a lot of difference between the training and the non-training data set, it is very easy for the adversary to know who belongs to the training data set and which sample does not belong to it. Because there's so much of difference, it is very easy for him to know. So we basically want to make sure that the difference between these two, whether you give a trained data set for inference or you give an unseen data to the model for inference, the output should not be drastically different. So we try to minimize this kind of a difference between them, which will help us to avoid this kind of an attack. So if we achieve that, it becomes very difficult for the adversary to determine that where exactly this observed data record belongs to, whether it belongs to the actual training data set or it belongs to the test data. It becomes very difficult for the adversary to know that. So because of this, the risk of the membership privacy loss is reduced. And they also claim that the classification accuracy of the model will not be affected, or it might be just slightly negligibly affected by using this method. And the utility cost of defense, like the classification accuracy loss, is also very negligible. So they formulate the loss function of this classification model as the loss of f of wi and bi, where wi is the weight per layer, I can be seen as the layers per layer, and b is the bias, x is the input, and y is the label. And the constraints are such that the weight belongs to the cardinal set of the weights. Here, ni is nothing but the number of non-zero values you want to have. So you will have a set which you do not want to prune. It's subject to that. And ni is the number of non-zero values that you want to have. That can be defined as nothing but the argmin of the max of this gain, the GF of the adversary. So we want to kind of maximize the gain, and we want to use the min-max strategy like we just explained, so that we can minimize that and find the best pruning strategy. We can think of ni as a pruning strategy because it is nothing but a set of non-zero weights that we want to retain in the model. The remaining we want to be pruning away. So that acts as the value over here to find the cardinal set of the pruning weights. So this serves as the loss function of the classification model. Next, what we'll do is we'll try to combine the weight pruning and the min-max gain against the model inversion attack. So while combining that, our objective remains kind of the same, except that this one term is going to be added here, where the gamma is nothing but the weight of the maximum gain of the inference model, because we want to find the best possible adversary model and we want to kind of minimize our risk against it. So that's why we are using a max over here of the gain, and the constraints remain the same. And here I've just described the terms. So this is how they have two. One is the MIA pruning loss function, and the other would be using the game theory kind of concept with using the min-max game against use the model inversion attack. So while these are the loss functions that we have, next let's talk about the solution strategy that the paper talks about. So first of all, the number of non-zero weights, the NI set. So how do we find that? So the main goal is to find the optimal compression ratio, or the NI. So for that, what the paper does is they choose a different NI in a range, like NI min to NI max. So they choose a range of data, the range of values, and they kind of randomly choose NI. They go about every value in the set and they choose an NI which can achieve the minimum gain. because that's what we want to achieve. So that is how we set the pruning strategy or the non-zero weights. So when we talk about the min-max game, the minimization of the maximization problems, they need to be solved jointly here to reach the equilibrium point, because we want to we want to minimize the maximum gain of the adversary model. So that's why we kind of solve it jointly. And for the current FA, we minimize the loss to find the most defensive model F against FA. Like I just explained in the figure, we want to find we want to minimize the loss in such a way that we want to find the best possible method that can avert the FA to happen. So, however, it's really difficult to solve the optimization problem of F directly because of the arguments that we have. So this paper tries to use some modified ADMM strategy to solve the problem. So this is the strategy that they use for solving this. Okay, next I have, okay, before I go to the solution, the convergence part, I'll just briefly describe how the algorithm works. So in the process, like we just described, we want to find a good pruning strategy to overcome this. So let's say Ni, we set a range of, let's say, n min to n max, and we iterate through this entire loop and see which is the best possible Ni. So for any set number of epochs, and for the t number of iterations, that is because you want to go layer by layer, you can choose a random mini batch for D, which is a training data set, and you can also find a random mini batch for the S prime, which is your from unseen data set. And you want to update the FA, the adversarial model's objective, to minimize the gain that it uses using, it's actually SGD, but it's a typo, they made it SDG. It's supposed to be stochastic gradient descent. They try to do the training and update the FA. And at the end of the iterations, they also try to find another random mini batch. This is just like the test kind of a data. They use this to update the loss equation to do this. So to update this, they kind of find another mini batch and they go through another set of training. And then they'll be able to find the optimum weight here. And then they do the pruning here using the PI. PI is nothing but the pruning matrix of that particular layer, the ith layer. So they apply the mask and they do the weight pruning at that method, at that iteration or that epoch. And then for the output, you have the weights, the bias, and the gain function. So this way, we can continue through several epochs and several iterations until you find the best possible strategy of the pruning. And that will eventually fetch you the minimized gain, which is the min max that we were just talking about. So you can get the WI star, the biases, and the ideal gain that you want. So this is how the algorithm works. Next, I'm going to talk about the convergence analysis. Do you have any questions so far? Okay. So for the convergence, these are some of the terminologies that they're using. First is the target network f of x, the main model that is being trained, which we'll be using as a target to perform the attacks. So this is the target network f of x, and sigma is setting with the activation function over here. And the original network that was used is the g of x, and the pruned network, let's call it the g hat of x, which is nothing but using the pruning matrix masked with the current weights per layer, and this goes on this way. So these are some of the terms. So for this kind of a strategy, they propose a theorem.
So what is the target network here?
The target network is nothing but the model that you used for training. Just this one. So one that was used for training. We'll try to target this model itself. The adversary will try to target this model to get the classification information.
I mean, what's the difference between? Can you go to your? That's what's the difference between target network and original network?
Okay. So this is
I thought that you already have a target network. That's the original. The target network is more like the original network. You want to transform it into a pruned one, which is robust against MIA. So why you have three? What? So that's why you have target network and original network.
Okay. So the target network is something that was used in the training that will remain
Yeah,
unchanged.
yeah.
So I think that the prune network G had just to say that during this iterations, because that will keep changing. That's why I think they kept one F and one G. One is something that remains unchanged. The other one is something that keeps changing because according to your pruning strategy.
So you mean the G? Uh, in the algorithm, can you go back to the previous slide? In the algorithm, where did we use the GX? Where did we use the FX?
Fx will be used here in the gain formula.
Yeah,
Yeah,
yeah. I see
yeah,
this.
here. Yeah,
Yeah, I see the F here. So where did you
yeah.
use the G here?
Uh,
The GFA or
no, it was still Fa over there and not the G. I did not see them using the G as such anywhere else. They've just used the G hat to imply the target model, the prune
uh-huh.
model. Um,
Maybe
it's
you can
like,
go. Yeah, I
yeah,
mean, maybe you can go. Anyway, yeah. I mean, if you can go to the paper itself, maybe they can give you
mm,
more information. I guess that I'm not sure what's the or is just used for the convergence analysis. I mean, sometimes they just if we want to analyze the convergence, we may want to define some additional symbols. So that's mathematical notations. I'm not sure whether the G maybe is more like some intermediate mathematical notation for you to derive the convergence or things like that.
yeah, I believe so because this was only used in case of the convergence analysis. Um, so
So
I
the
saw them use this in the analysis of a neuron. They have a part where the f of x will just corresponding to the wfx, but
mhm,
G would also include the activation. The F somehow did not do that. But when they define it, they say that it's the target model and the network model. But
mhm,
in the convergence, yeah, they use it kind of like a intermediate model,
mhm.
the one with activation. But but they have not used that anywhere else in the algorithm or anything as such.
Yeah, I just have a quick view of the kind of the paper.
Mhm.
The first time I saw the G just in the theoretical analysis, I didn't see that elsewhere. Just the convergence analysis, they define a G. Maybe they
Yeah,
did it just for convergence analysis. So
yeah. Maybe I can just show this part. Uh,
yeah. Anyway, yeah, you can just yeah. I
yeah.
just be curious about what's going
Oh,
wrong there.
okay. Okay. I mean, I just wanted to show this part where they define the target network as f of x, and then the original network to show that where the wi would be for the ith layer, and the wj will be for the jth layer corresponding to gx. So maybe they wanted to show it like layer by layer. So that's why they used a different one other than f for g. I'm just thinking because
Why?
yeah.
Why there's a if you check the 4 and 5, looks like
Hmm.
for the original network you have just one layer, n layer, and then in G you see the rotation is 2n, right? That basically means that I
Yeah.
have 2n layers,
Um,
and then the proved network is also the
twin.
G hat is also 2n.
Yeah.
Oh yeah, they define. If you say that they can you say the theorem 1 consider G defined in equation 12 is a randomized initialized neural network with 2n layer
Yeah, it's actually the same.
They have the definition. You see.
Yeah. Yeah, they have actually repeated the same thing, the same equation here. The 11, 12, and 13 are the same as the 4, 5, 6.
I guess this is related to the pruning. In practice, how do they do the pruning? So they may, maybe it's kind of common in their literature that you define a G corresponding to F, and then you're trying to prove G to get a G hat. This is just my guess because I'm not working in that area. So, but they do have some kind of explanation there. You may want to check it later. Yeah.
Yeah, yeah.
Okay.
Okay.
Yeah,
Yeah.
I have another
I
question.
think.
Like,
Yeah,
oh,
Shannon.
sorry, you can finish your sentence first.
Sorry.
You want to finish your sentence
Oh, no,
first?
no.
Oh,
No,
okay.
please go
I
ahead.
just want to know that why there's 2N in the G and N in the F.
Okay, so one thing that they use that is for to say that if you have a simple neural network, then your f of x will be nothing but the w times x. You are not going layer by layer. But when it comes to G, you want to go layer by layer because you want to prune it. So it would be like you can look at something like this. So the g of x at that time will correspond to the summation of all the weights in that particular layer times the input that you want to give. So I think because you're going like from layer to layer, I think that's why they gave it a 2n versus the target model, which we do not see to change at all. So that's why it has as n.
Okay. Thank you.
Okay. So going on from whatever we concluded about F and G, in the theorem that they propose, they consider that for a randomly initialized neural network for 2n number of layers, where you have the D as the input size and n is the number of layers, and defining the maximum number of neurons in a layer, you see that the original model, the target model, the difference between that and the prune model, and the supremum norm between them should be less than or equal to the epsilon that you set. So this is the kind of theoretical analysis that they provide, that they say that because of this, it provides some amount of privacy because of the randomness. So they say that this will also further help them to improve the performance compared to differential privacy or the game theory. So the other conclusion we can get out of this is for every bounded distribution that you have, and for every target network which has bounded weights, so there is always a subnetwork which has a competitive accuracy of the original, which is sufficiently over-parameterized. So compared to the original, in the big model, you also have like a subnetwork out of it, which will perform equally as the main network. So this is something like the lottery ticket hypothesis papers, where they say that out of a big model, you can, or after pruning, you can find several smaller subnetworks, out of which some can be trained in such a way that they perform as well as the original model. So the goal here is the same, that they try to find such kind of a subnetwork, and this is the analysis that they have for that.
Pavana, so it
Yes.
seems the 2-layer and 2n layer and the 1n layer assumption, they do the assumption here, right, in the theorem. I'm not sure this
Yes.
assumption is for the easiness of theoretical analysis, or it's kind of common things. When you do the pruning, you have general assumption like this. I mean, yeah.
I have seen this kind of assumption before, Dr. Pan, in some other pruning papers as well. So I don't know the exact explanation as to why they do that, because I feel it is mainly because you will significantly keep pruning it, like you'll keep removing the weights of it. So you will have to like do a back propagation. So you go through n layers and then you kind of do a back propagation. So it becomes like 2 times of the layers. So I feel that that's the reason why you have the 2n kind of consideration when it comes to only the pruning part.
I won't say that this theoretical analysis just like in this slide they show that in the last sentence this is a over parameterization neural network graph. In this kind of area domain they build a lot of assumptions just like this one to get the theoretical analysis. I mean these are traditional assumptions in over parameterization neural network.
So that's for the easiness of theoretical derivation, right? It's in
Yes.
practice probably we don't do this.
We don't do this.
Yes, yes.
Yeah, please continue.
Okay. So far we were looking at the training part and the algorithm of how we try to build the network. So now we speak about the inference model. So the gain of the inference model FA can be seen, it can be rewritten as instead of the previous equation that we saw, instead of this one, we can rewrite this using the probability distribution instead without changing any of the values here though. So we transform this to this kind of equation because there is some optimal determination solutions for such inference models was proposed in these 2 papers from NIPS and the ZigZag conferences. So in that, they say that the optimal solution for the FA star can be given in this way, which is nothing the probability distributions of the original model versus the X prime from the unseen model. So we use this kind of concept and we try to transform this gain function to substitute the optimal FA as FA star in the gain function to obtain this kind of an equation. So after simplifying this, we obtain this relation where we see that this kind of difference is nothing but the Jensen-Shannon divergence between the 2 distributions PF and PF prime. So what is the speciality of this is we know that the Jensen-Shannon divergence usually is non-negative and it will be equal to 0 here only if these 2 are equal. So basically if the probability distributions between this, the predictions between the 2 distributions would be the same is when this will become 0. So if this becomes 0, then our gain is the minimum value of the gain would just be like minus log of 4. So why is this important to know? Let's just see that. So the observation is now, let's say, just for easy representation, let's call this entire Jensen-Shannon divergence part as a D. So let's use that D to just show the divergence between the probability distributions of the outputs of the F. So the prediction of classification model for both the training and the non-training set, if they have the same probability distribution, what happens is, it means the classification model can be totally protected from the model inversion attack because the adversary mainly relies on the difference between the performance of the model for the training data and the unseen data. Using that is how it leverages to do the attack. Now, if we make the difference between that so minimum or almost 0, which means that we can totally protect it from the model inference attack, membership inference attack. So also the relation also implies that if you have a large D, the large distance, which means that there's a higher maximum gain obtained, which means that your classification model becomes more and more vulnerable to the attack. So basically, if you have any methods which can minimize this difference and make a very, very small D, it can have a scope of defending such membership influence attacks. And intuitively, if you think about how weight pruning could participate in the same thing, so weight pruning, as we were talking, will prevent overfitting because it prevents the overfitting. The difference between the outputs of the training and the non-training set will not be a lot. So the D will be small, which also shows that how it will be able to defend against the model inversion, membership inference attack. So these were the observations of how they theoretically show how this works. Next, I have the simulation part. In the evaluation, they look at 2 perspectives. One is what's the defense performance of the model against the attacks, and other is the computational cost benefit that we obtain because we are pruning and reducing a lot of parameters and we're reducing the model size, etc. So for the simulations, they use 4 different models, the LeanNet5, VGG, ModelNet2, and ResNet18. And for the datasets corresponding to those models would be MNIST, Cypher10, Cypher100, and ImageNet. And for the baselines, they use their own MIA pruning depicted will be their own method. And the second would be the plain training of the classification model without using any adversarial training or without using any pruning strategy, just the plain training would be one baseline. The other would be to use the game theory concept, the min-max game. And the other would be the differential privacy. And here for the DP, they use the epsilon as 6.28 in all of their experiments. So with these experiments, they say that comparing the classification accuracy, that is nothing but the test accuracy, versus the membership attack accuracy on the different image data sets, they say that the MIA pruning, their strategy is performing much, much better. So the testing accuracy is also very high. If you compare it with the plain testing or the game related thing, their accuracy is very good. And also the attack accuracy, which we want it to be very less, it is also very, very less for almost all of the data sets and all the models in comparison with both the plain training and the game. Only in, yeah, it's, so we see that there is a gain in both benefit of both performance retaining and privacy preserving. We'll see some further evaluations on when they did the inference attack models. This is comparing the DP and the MIA pruning. We see that the classification accuracy for DP is actually much lower compared to their strategy. And their attack is also, the DP's attack is a little higher than their strategy. So we see that MIA pruning is kind of outperforming even DP in terms of smaller data sets like MNIST and Cypher. And also we see a similar behavior when it comes to larger networks and larger data sets like ImageNet over ResNet, etc. So we see that the weight pruning overall has significantly less utility cost as well compared to DP. And that was about the attack perspective. Now talking about the computations, how it lowers the computations, because it has anyways reduced the model size. We see that for the models, these are the original weights for each of them. We see that they're very big, especially the VGG or the ResNet are very, very huge with containing millions of parameters. So after pruning, the weights are reduced substantially, and correspondingly, the weight reduction ratio will be this way. We can achieve up to 15 times lesser weight reduction compared to the original model. So the advantage is because we have reduced the model size so much and the remaining weights are much smaller, they can be probably deployed on smaller devices like mobile devices. So while this was about computations, looking at the loss and attack accuracy, we see that the membership attack accuracy during the training, during training the inference model, gain the train classification model, it is much, much better. The MIA pruning is their strategy. We see that it also converges quite rapidly in just about like 20 epochs. We already see that it has converged compared to the other methods where the convergence is like much slower. And also with the attack accuracy, we see that it has much lower attack accuracy and also a little bit earlier through the training with lesser number of epochs, we see it performing well. There are some other extra experiments. This was just to show the distribution of weights, because after pruning, we see that the weight distribution will be much less. So both MIA pruning and MIA pruning along with the min-max concept imbibed, we see that the weight distribution is much smaller compared to without pruning. And if we were to talk about all the advantages we just saw for the MIA pruning analysis in general, we see that for the same type of model, if we see any model is more overfitting, which means it is more vulnerable to the membership inference attacks, and least generic the distribution of the data is, which means more information it leaks. So it is better to be more general. And the MIA pruning also achieves the parameter sparsity by pruning all the unimportant weights. That's why it can reduce overfitting, which can be caused by overparameterized networks. And the difference between the prediction between the training data and the testing data can be learned by the inference model. That's how it is able to distinguish the membership. So this is the main part that is used by this paper to overcome the attack. And since models with pruning in Minimax or Minimax game can reduce overfitting. That's why they have a lower prediction certainty compared to the training data. And also, the larger the training, the non-training gap is, like the accuracy gap between the training and the non-training data sets, then the higher would be the membership attack accuracy. So this is the summary of whatever we just saw, both in theory and in the experiments. So finally, concluding what we saw today, in this work, we formulate jointly the weight pruning and the membership inference attack as the MIA pruning, and they provided an algorithm to solve this problem. And they theoretically analyzed and also concluded that the proposed algorithm can protect some information privacy from the membership inference attacks and also achieves some competitive accuracy. And from the experiment results, they see that the weight pruning can significantly reduce the information leakage. And thanks to the hardware-friendly characteristics of the weight pruning, where the weight storage and the computation operations are drastically reduced, the proposed MIA pruning can be very helpful for deploying these DNNs on mobile devices. So that's all I have. Thank you for listening. If you have any questions, please ask.